Fundamentals of Measurement and Calculation. In this supplemental video, I will demonstrate to you some problem-solving techniques involving dimensional analysis and ratio and proportion. Most word problems can be solved by closely analyzing the given data. There is no shortcut to effectively arriving at the correct answer. A useful technique that is commonly performed in solving problems is called dimensional analysis. This technique basically involves the logical sequencing and placement into an equation of all of the arithmetical terms, including both quantities and units involved in the problem, such that all of the units cancel out except the units of the desired answer. By this method, ratios of the data are used, conversion factors added as necessary, and individual terms inverted to their reciprocals to permit the cancellation of like units in the numerator or numerators and denominator or denominators, leaving only the desired term or terms of the answer. This technique permits one to solve a word problem without the use of extensive or complex formulas, and also it allows the consolidation of multiple arithmetical steps to single expression. However, one must be extremely careful in lining up these arithmetical terms, so it is necessary that units are always included in calculations. Having units in calculations or solutions also allows us to review our solution to find possible mistakes when the final answer becomes ambiguous or superfluous. In order to illustrate the process of dimensional analysis, let us try to solve some problems. First problem: how many fluid ounces are there in 2.5 liters, where 1 liter is equivalent to 1000 milliliters and 1 fluid ounce is equivalent to 29.57 milliliters? In order to solve this problem, first let us identify the given items or the given values. First, we have the 2.5 liters. We are asked to convert that quantity to fluid ounces using the conversion factors that are encircled on this slide. Because we need to find the equivalent fluid ounce of 2.5 liters, we will begin with that quantity, 2.5 liters, and then we write on the other side of the equation the unit that is desired. And the unit that is desired is in fluid ounces. Next up, we will then identify which of the given data, including the conversion factors, will give us the unit of the desired quantity. And that is this conversion factor. 1 fluid ounce is equivalent to 29.57 milliliters. In order to cancel out the units liter and milliliters, we need to use the other conversion factor, which converts a liter to 1000 milliliters. Next, we cancel like terms, liter, milliliter, leaving us only with fluid ounce. The final answer will be 84.5 fluid ounces, or we can round this off to 85 fluid ounce. We can also perform a calculation where we use ratio and proportion. Take note that 2.5 liters can be converted to 2,500 milliliters through the conversion factor. Now, what we know is that 1 fluid ounce is equivalent to 29.57 milliliters. We need to determine how many fluid ounces X are there in one 2.5 liters or 2,500 milliliters. Now we will just do cross multiplication, or we will simply multiply both quantities on the left side of the equation by 2,500. We get the same answer, 84.5 fluid ounces, or equivalent to approximately 85 fluid ounces. Question number 2. A medication order calls for 1,000 milliliters of a dextrose intravenous infusion to be administered over an 8-hour period using an intravenous administration set that delivers 10 drops per milliliter. How many drops per minute should be delivered to the patient? Just like what we did in the previous item, let us identify the given quantities. We have 1,000 milliliters, which are to be given for an 8-hour period. The administration set delivers 10 drops per milliliter of the medication. The quantity that is desired is in drops per minute. Now, in order for us to set up our equation, let us first write the unit of the quantity that is desired. And in this case, it is in drops per minute. In order to line up the quantities in our dimensional analysis, identify the units that are present in the final quantity. We need drops to be in the numerator. So that means we will put drops coming from 10 drops per milliliter in the numerator as well. Next, in our final quantity, we have minutes, a unit of time in the denominator. That means any unit of time that we have in our given should be in the denominator as well. And in this case, we have 8 hours. Remember that the medication, which is dextrose intravenous infusion, must be taken over an 8-hour period. And the volume of the medication is 1,000 milliliters. So we can place 1,000 milliliters in the numerator. So we need to take 1,000 milliliters of the medication over an 8-hour period. Now we know that 1 hour is equivalent to 60 minutes. This is the conversion factor that is necessary in order for our final quantity to have the unit minutes. Next, let us evaluate if we can already cancel all the units except for the unit that is in the final quantity. We can cancel hour. We can also cancel milliliters. We will be left with number of drops per minute. In this case, we can now perform our mathematical operation. 1,000 times 10 divided by 8 divided by 60. And that will give us an answer that is equivalent to 20.83 drops per minute. Now, we can approximate this value to 21 drops per minute because logic tells us that there can only be whole number of drops. If we will consider the rules for rounding off in this particular item, we have to round off our final answer only to contain one significant figure. So we can further round this off to 20 drops per minute. That will be the final answer. Did you get it right? Let's try some more. Question number 3. A formula for 1,250 tablets contains 3.25 grams of diazepam. How many grams of diazepam should be used in preparing 350 tablets? Just like what we did in the first question, we will identify the given quantities. We have 1,250 tablets, 3.25 grams of diazepam, and 350 tablets. Remember that 1,250 tablets contain 3.25 grams of diazepam. And what we need to find is the number of grams of diazepam present only in 350 tablets. So, in solving this using dimensional analysis, we begin with 350 tablets. Again, we know that 1,250 tablets contain 3.25 grams of diazepam. Here, we can already cancel out the number of tablets and we already have our final answer in grams. Multiplying 350 by 3.25 and then dividing the answer by 1,250, we get 0.91 gram. We can also calculate this using ratio and proportion. Using ratio and proportion, we take note the given 3.25 grams of diazepam are contained in a formulation for 1,250 tablets. Now we are asked to determine how many grams of diazepam X can be found in 350 tablets. Performing cross multiplication or multiplying both quantities on the left side of the expression and on the right side of the equation by 350, we get the value that is 0.91 gram. Okay, let's move on to the next question. Question number 4. A cough syrup contains 2 milligrams of brompheniramine maleate in each 5 milliliter dose. How many milligrams of brompheniramine maleate would be contained in a 120 milliliter container of syrup? Just like what we did before, let's identify the given. 2 milligrams of brompheniramine maleate present in each 5 milliliter dose. We are asked to determine how many milligrams of brompheniramine maleate would be contained in 120 milliliters of the syrup. So we will begin with 120 milliliters of the syrup. And then we know that we want to determine the number of milligrams of brompheniramine maleate. In order to cancel the milliliters, we use the dosage strength that is given, 2 milligrams of brompheniramine maleate contained in each each 5 milliliters of the syrup, we cancel the number of milliliters or the unit of milliliters, and we now arrive at our final answer, that is 48 milligrams. Just like before, we can also calculate this using ratio and proportion. We know that 2 milligrams of brompheniramine maleate are contained in 5 milliliters of the syrup. We want to know how many milligrams X of brompheniramine maleate can be found in 120 milliliters of the syrup. We calculate for the value of X, and that will still be 48 milligrams. Let us now proceed to the last question. If an intravenous fluid is adjusted to deliver 15 milligrams of medication to a patient per hour, how many milligrams are delivered per minute? Okay, so what is your answer? Just like what we did before, we will identify the given quantities. 15 milligrams of the medication are to be given in an hour. You are asked how many milligrams of the medication shall be delivered in a minute. So, in solving this problem using dimensional analysis, let us begin with 1 minute. We know that there are 60 minutes in 1 hour. Also, we know that the rate of delivery of the medication is 15 milligrams per hour. Now, let's see if after we cancel all the units, we will arrive at number of milligrams. We cancel the minutes, we cancel the hours, we will be left with number of milligrams. So we can now multiply 1 by 15 and then divide this by 60. We get the answer 0.25 milligrams. Just like in the previous questions, we can also solve this problem using ratio and proportion. We know that 15 milligrams of the drug can be delivered in 1 hour. We need to know how many milligrams of the drug can be delivered in a minute. We can either convert 1 minute to an hour or 1 hour to the minutes. So let's choose 1 hour. 1 hour is equivalent to 60 minutes. Now we solve for the value of x. X therefore is equal to 0.25 milligrams. I hope that you got all the questions correctly. That ends this part of the supplemental video. Good luck.